So when we see scatter plots, we can describe that idea of the direction and the strength of the data. However, what we want to be able to do is also describe those features using just a number. And that is our linear correlation coefficient, which we denote by the letter R. And for notation, R is our sample correlation coefficient. And if we had population data and we were finding this linear correlation coefficient, the symbol that we use is the Greek symbol rho. It's kind of like a curvy P. But rho, this would be our population correlation coefficient. But as always, we'll typically have sample data that we're looking at. However, those two symbols do work together to represent the same thing. It just depends on what type of data you're working with. So notice that this is linear correlation coefficient. So we're going to have some conditions as we move forward. And one condition that we should be checking is that our data is roughly linear. So we'll be looking at the scatter plots to make sure that we should even be talking about R, because if our data has any sort of curvature to it, or if it's just hard to see any sort of linear trend, we don't really want to talk about something that describes behavior linearly. So that's going to be a condition we need to check along with a few others that we'll talk about. So this number R, there is a formula for it. There's two ways you could look at this formula. But essentially, these are the formulas, but we're going to use technology to do it. So in the next video, I'll go through using technology to make our scatter plot and finding this value for R. But these formulas, we're not going to worry about actually calculating with them. So when we use technology and get a number out for R, here are some characteristics of what we're going to see. R is a number that's between -1 and +1. It'll always be between those two values there, inclusively. We could get R equals -1, we could get R equals +1. Something we're going to do is talk about this scale down here. And actually where I have arrows, that should probably just end at -1 and at +1, since it can't continue on. But the idea is this value of R is going to land somewhere on this number line, and where we land tells us about our scatter plot, tells us about this direction and strength of our data. R has no units, so in terms of putting it into a sentence, we won't really describe the number itself. What it's going to tell us is, do we have strong, moderate, or weak data? And it's going to tell us whether we have a positive or a negative association. And so that's how we'll put it into a sentence, is just talking about strength and direction. But the number for R, we can't really interpret in a sentence. The closer R is to -1 and +1, the stronger our data is. So it's out here. When we land with R, somewhere out here, we're going to have a strong strength. And then as we move closer and closer to 0, the weaker it gets. So what we're going to see is strong data, then it becomes moderate, and then it's here that we have very weak data. Then what we also have is the sign of R. So everything over here on the left-hand side is negative, everything over here on the right-hand side is positive, and that's telling us the direction of our data. If R is negative, then we're going to have a negative direction. If R is positive, then we're going to have a positive direction. So let's split up this number line and see how these scatter plots are going to work. So between 0 and +1, this is where we'll have a negative direction. So if we land in this region with R, we are going to have a decreasing trend for those graphs. And then as soon as we switch over here to positive, then we'll have our positive direction. So if we land on this right-hand side, all of these graphs are going to be increasing. What happens at 0? This is our neither scenario. And then if we have R equals 0, what our scatter plot would look like this would be our blob scenario where there's just no trend to it. Then, in terms of strength, so r equals -1 and r equals +1, this is where we have the strongest strength. Meaning at -1, if we had r equals -1 as a scatter plot, this is going to be perfectly linear. That if we drew a line, the line would go through every single data point. And it's negative, so we'd have a decreasing trend to it. So we would see something like this at r equals -1, where it makes a perfect line. And then at r equals +1, this is where we'd have a perfect line of data, and it would be increasing. So this is where we have the strongest strength, and then as we move towards this middle here, it becomes weaker and weaker. So some cutoff points that we want to use is the halfway mark at 0.5, so -0.5, +0.5. And then another cutoff point we're going to use is at about 0.8, -0.8, +0.8. And what we do is anything that's between -1 and -0.8 in the strong region, that's going to have a strong strength to it. And same thing out here at 0.8 to +1, this is going to be strong. So what this means is if we have scatter plots that are landing in this region, our R value puts us there, we're going to see that strong graph around that line. It's just going to have a little bit of scatter to it, and if we're over here, it's going to be decreasing. If we're over here, it'll be increasing. But overall, that data should look very linear if we're landing out there. When we land in between -0.8 and -0.5 and +0.5 and +0.8, this is where we get the moderate strength. So this is where our data still looks pretty linear, but there's more spread to it. So if we had scatter plots here, what we might see is we'd have our decreasing trend. It just spreads out a little bit more. And then here we'd have our increasing trend, and it just spreads out a little bit more. And then as soon as we're in here, -0.5 up to +0.5, this is our weak strength. This is where there's a lot of spread to our data. So in here, maybe it looks barely linear, but overall, it's verging on that kind of shape of this blob of data, but maybe there's the ever so slight positive trend here, but pretty scattered. So when we get this value for R, what we want to do is take that number that we get for R from using technology and see where we land on this number line. So if we had R equals -0.7, we would say, okay, -0.7 lands in here. So our data has a negative direction and a moderate strength to it. We get those two pieces of information just by landing on a spot on our line there. So we're going to go through an example, and what I would like to do is talk about the coefficient of determination first, and in the next video I'll go through this example and showing how to use technology to get this value for R, and also take a look at that scatter plot so that we can check our conditions without having to graph it by hand. But let's talk about the coefficient of determination, which is R squared. And that's a literal squaring of R. It's whatever number we get for R, we just square it, and that tells us our coefficient of determination. And be careful with these because coefficient of determination and correlation coefficient can sound very similar, so just be sure you're matching up the correct values when you're using R versus R squared, because numerically they're going to be different. What you're going to see in various sources is they switch between lowercase r squared and uppercase r squared. There's no difference. This isn't the difference between sample and population. They're both representing the same thing, it's just the notation switches around in some locations. So what the coefficient of determination tells us is the percentage of the variation in the y values that can be explained by the least squares regression line of y on x. Or more simply, it's the percent of variation in y that can be explained by x. So what this does is it's another way of talking about the strength of the data. How much are they relying on each other? It's kind of this percentage of reliance of how y is changing based on x. So something that we're going to see from technology is that we get r equals 0.8135 for those chirps per second. And what we would do to find that correlation coefficient of determination is we would square that value for r. So r squared, we would take that 0.8135 and we would just square it. So r squared is 0.8135 squared, plug that in the calculator, and that's going to be about 0.6618. And what this tells us is that 66.18% of the variation in our y variable, or in our response variable, which in our case was the chirps per second. So in chirps per second, can be explained by our independent variable, which our independent variable x was temperature in our case. So it's describing that percentage of reliance on how our chirps per second change based on temperature. And then the rest of the 100% is based on other factors. But we can relate this 66.18% of it to the other variable, temperature. So it's describing how they rely on each other. In the next video, I'll go through technology of how do we get that 0.8135, making sure we interpret it correctly with our example.